Hi, this is Dan Bullard doing another video for you. Front deck of my houseboat, and it's a beautiful day on the river. The sun's shining. It's always a beautiful day in Oregon when the sun's shining. I want to talk about some specifics with Bullard laws of harmonics, Law 1 and Law 2. Law 4 fits in there as well. And I've got a couple of articles that I've written that are going to help prod me through this. And I've got my heater here, so don't mind the hissing, it just keeps me warm. I know the sun's shining, but it's still January. I like taking a wave and chopping the top off, or chopping the bottom off. And like, here's an example, okay? Chop the top of the wave off. In this case, it's 4% of the wave, so that's 400 points. I have a 10,000 point transfer function. Now I'm not chopping off 400 points from the wave. That's up to the wave when I do the VLOOKUP table, and there's an article on how I did that too. But so chop the top of the wave off, and then, or I chop the top and bottom of the wave off, and then I'll do some really cool things with an FFT. So I'll do an FFT on it, and then I'll go in and I will add 6 dB to the harmonics, right? Leave the fundamental alone, add 6 dB to the harmonics, or take away 6 dB from the harmonics. And what will happen is it'll change the shape of the wave in a very specific pattern, okay? It's really cool, I just love it. And what this does is it proves, for example, I did another one where, and here's an example, I do a crossover distortion, simulated crossover distortion, where I'm doing the zero crossing. I take out a chunk as though I were doing a broken class AB, where the biasing on half of the thing is broken, okay? It's the way you find out things, okay? You simulate malfunctions to cause something to happen, and that gives you an idea what's going on. You know, looking at these things on a scope, you know, like the guy at Tektronix who told me an FFT is just a button on a scope. Oh my God, that's the stupidest thing. Park is just a P on a steering wheel. Oh yeah, no, it's where you put your car, okay? It's not just the letter P on a shifter control, okay? So an FFT does the Fourier transform, and an inverse FFT does the inverse Fourier transform. So what I do is I'll take this distorted wave and I'll chop the top off, or chop the bottom off, or chop them both off, and then I will go in and do an inverse FFT, do an FFT, then modify the harmonics by 6 dB, and then do an inverse FFT, and you get the wave back. And you get some beautiful pictures. I mean, it's just gorgeous. So here's an example. I did one, and I've done several of these. There's several articles that I've written that do this. So I have this one, beautiful waves. And that's because I chopped the top and bottom of the wave off, and then I added or subtracted 6 dB to the harmonics, and that fixed it. That made these beautiful patterns. Now when I do the zero crossing distortion, you can prove law 1. Boom. I mean, it's like, you know, I hate measuring area of a curved thing because it's like integration and all that crap. But with the crossover distortion, it turns out to be beautiful because it's a perfect triangle. So you start with a perfect triangle chopped out of a sine wave, and then you add 6 dB to it, and it makes it go the other way, and it's beautiful. It's just, so that proves that law 1 is true, okay? Now, a lot of people sort of think that, right? That if you said, well, law 1 the area of the distortion controls the amplitude of the harmonics, they'd probably believe that. That's kind of why they're doing THD, which is the most ridiculous thing I've ever seen. But at least Law 1 does address it, and most people sort of believe it. But Law 2, that's a biggie, Law 2. Law 2 says that the angle where the distortion happens controls the harmonic signature, okay? And that's something you just don't get on a scope properly if you have in the FFT mode or whatever. The right way to do it is to look at it in simulation, okay? And so when you look at this, and I'll show you a picture, here's an example that shows the angle at where all these things happen. Notice the angle is the same no matter what I do. The angle is always the same. The distortion starts and stops at the same place no matter what. And that's true with the other one too, where I do the zero crossing. So it's the angle that controls the harmonic signature. And if I change the values in the harmonics and be true to the harmonic signature, I maintain the angle. So it's the angle that tells you what the harmonic signature is going to look like. And that is crucial. That is absolutely crucial. Now, I can't make you read the book, and I never ever give away the Bullard harmonic solution, although I'm sure someone will publish at some point. And I'll sue the hell out of them for that. But the Bullard harmonic solution gives you the formula which predicts what the harmonic signature is going to look like based on the angle where the distortion happened. Chapters 3 and 4 cover the applicability of the Bullard harmonic solution. And again, I came up with it myself. I'm going to hold on to it. I almost gave up on it. I couldn't figure it out. It's like, math is not my strong suit, but this one, it took a while. And then I finally figured it out. Boom, got it, nailed it. Nobody else has it. Nobody. So anyway, the articles were more fun with inverse FFTs, and the other one was symmetrical crossover experiment. So you'll really, take a look at those articles. I wrote them for a reason, and I have them backed up, so if LinkedIn deplatforms me, they're backed up on my main website that you can go look at, www.danbuller.com/Dan/DSP, or just go to danbuller.com and look around. You'll find any place where I talk about DSP. Boom, there you go. So a lot of good stuff there, I think, and hopefully you'll learn something. I think you will. I've been doing this a long time. Been doing training since I was 19, 20 years old, so I think I know what I'm doing. Anyway, thanks for your time, and we'll talk to you later.